So yeah, I have quite a lot of slides, so I'm going to try to keep the presentation short. I might skip some of the slides today. So basically, I'm going to start with a little heads up. So fast outbound is basically a new feature which we are proposing for ZFS. So as a heads up, this is only a design proposal, so there has been very little code written so far. It's mostly a quick review to done with Imation to see the feasibility of this project. So essentially, what fast outbound is basically a almost instant file copy. So instead of duplicating all the blocks that we are copying, we're basically only referencing the same blocks from different places. So what are the motivations for this? First of all, the motivation is to support the VMware VAI support. So for those who do not know, VAI basically is an API which is designed by VMware, and it's basically designed to leverage some hardware acceleration functionality, and to make sure to offload some of the operations from VMware to the actual storage array. So in particular, there is two operations which can be beneficial, can benefit from the fast file clone, is the NAS full file clone and the NAS fast file clone. So I'm not going to go into much details what they are, but basically full file clone is meant to offload the copying process to the storage array, and it's an offline process, so it can take a long time, but it prevents the client from having to gather the data real and having to send it back to the network. So it's sort of just remove the load from the network. Fast file clone is mostly to support snapshots inside VMware, and basically to allow to make very, very fast snapshots. And now the other motivation is that allowing fast file clone is a way to save space in the disk. And even more importantly, it's a way of saving memory. Because if you have, let's say, 100 VMs which are running on your storage, and like basically 90% of the data on those VMs is being shared, instead of having those blocks, all those blocks cached separately in the memory, you basically cache only once. So you have much more free space inside your ARC. So there is some existing alternatives, and those are not really there to support fast file clone, but they sort of in the same area. One of them is dataset clones, and the other one is duplication. So I might talk a little bit later about those. Now, a little warm-up here for those who are not as aware about the ZFS underlying structure. So basically the way that the data is stored in ZFS, every file has a D node associated with it, and then under it we have indirect block pointers of, and then we have the data under it. So data is marked ABC. Whenever we do a file copy, we have to basically duplicate the D node with all its system attributes, then write down duplicate all the data blocks, and then link the D node to those data blocks. Okay, so now we're going to go to our first method. Yes. Just CP, yeah, exactly. Just CP. This is the regular CP. So now I'm going to talk about the actual first approach for doing the file coding. It's called the direct references method. So what makes the direct references method? It's very, very similar to the way snapshot works. So whenever we do a fast file clone, we duplicate the D node, the system attributes, and instead of duplicating the data, we just point back to the exact same data. So what happens when we add the data of our D node 2? So what we do, let's say we have data block 3, and we edit it, and then we make a block called the line. So we write down this block, then we have to propagate all the metadata, and then the data which hasn't been changed, we point towards the data which is shared with the previous clone. And then finally we update the block pointer for the second node to point towards this new data. So this diagram, for the next slide, this diagram is going to be a little bit different because having arrows everywhere is a little bit messy. So it's going to be presented more of this way. So here in the beginning we just perform the clone operation, and we have the data. It's the same data on both sides, marked with A. So on D node 2, we decide to modify some blocks, and now we have blocks B. Those are private blocks to the second D node. And the shared blocks are still there, and those are basically the same blocks as we see on both sides of the shared blocks. So this is the kind of diagrams we're going to use for the rest of the presentation. So what's the main concept of this file clone is the reference node. So the reference node, what happens is whenever we do a clone, we actually make two new denodes. One denode is for the new file, so which is named the clone, and the second denode is called the reference node, and this one is a hidden denode which also points to the original data. Now, what's the reason for that? Okay, so basically, whenever we have data which is referenced from different places, there is one problem which arises is to keep track of how many references do we have to this data. The motivation behind that is basically whenever we don't have anybody's references to that anymore, we want to free this data so we don't have any leaks. And this is very similar to the way right now snapshots and dataset clones work. So in terms of dataset clones, we have a read-only snapshot which has a reference to the original data, and then the dataset clones is made on top of that. So here, basically, there is another method for doing for tracking basically which blocks can be freed, and this is what is done in identification. They are using a ref count. We want to avoid this because a ref count implies that whenever you do a clone operation, you have to traverse all of your blocks and update the ref count to reflect the second topic. So we are avoiding that. So now here is a demonstration how our cloning what's basically the use of the reference node. So in the beginning we just perform the clone operation. So we have our original file denode 1, we have our clone denode 2, and we have our reference node. They are all pointing towards the same data. Now we update denode 1. We have some new private data marked as B. We update our denode 2. We have new private data marked as C. And now you may have noticed that some blocks are not being referenced anymore, and those blocks are shown here as garbage data. So this is where the reference node comes into play. It keeps referencing those blocks, so later on we can destroy them. Okay, so what do we need to implement this fast file clone is we need to add some new system attributes to our denodes. So there is two denode types for which we need to add those system attributes. There is the clone files, so they have a new flag defining that this is a clone. We have a new attribute saying what's the ref node for this file. And for the reference node, we have basically a new flag saying that this is the reference node. We have a list of clones. So here, I will talk a little bit later about this. A list of clones is basically an array of integers which are pointing to all the clones of this reference node. And finally, there is another attribute called birds. This is basically the TXG at which the reference node was born. And this is very similar to the birds parameter of a block pointer, except there is some reasons why we can't put the block pointer, and we need to actually have this separate attribute here. So on the next slide, we have basically just a list of all those new attributes. The same thing as the last slide. In here, talking about the clones, if it's too complicated to make the attribute an integer, a resizable integer of array, a resizable array of integers, we can also simply create a new zap object, and the clones will just point to the new zap object, which is going to contain the list of all the clones. So that's another alternative. Okay, so here we're going to go over the block freeing process. So basically, as you've shown, there is some blocks which are shared among the other clones, and some blocks which are private to this file. And our main key is that if we overwrite private blocks, we want to free them. If we overwrite shared blocks, since we don't know if they're being used by other clones, we want to keep them. So the general rule of thumb is that, okay, here, so here let's say we have our file. File 1 was created in TXG177, and then later on we cloned this file in TXG200. So this is when the reference denode was created. There's also a second denode that was created, but we can ignore it because we don't really care about it for this demonstration. So now, let's say in TXG202, we decide to modify the contents of file 1. So we modify the contents of file 1. Some of the blocks are not being referenced by this file anymore. So we try to see, do we need to free those blocks or not? So what we do is we compare it with the birds of the reference node, and since those blocks were created before it, we keep them. So we don't do anything with them for now. Now, let's say we overwrite again this data in TXG205, and we overwrite the previous blocks. So those are private blocks of this file, and we need to basically compare them again with the reference denote words, and since they were born later, we have to free them and get rid of them. And basically, so for freeing blocks, there is two general rules. Blocks which were born after the reference node, they are treated exactly the same as the regular blocks, so no differences from the way previously ZFS is working. And blocks that were born before the reference node, they're only freed when the reference node is destroyed. So basically, the reference node is destroyed whenever we destroy all the clones. There was an alternative to destroy it whenever there's only one clone left, but this adds additional complexity that we don't really want to do in the first version. And the advantages anyway are quite marginal in some cases. So now the interesting part is multiple clones. Let's say again, let's take the VMware as our client. So VMware is our use case. And what often companies want to do is to create one virtual disk and configure it. We're going to have a virtual disk file, and then we want to use this template to create many different VMs. So in our case, this is going to be file 1. So file 1 here, whenever we need to create, whenever we need to deploy a new VM, we just clone this file. So we have file 2 which is being created, and then we can deploy the VM on this new virtual disk file. So this virtual disk file is being modified. We don't care about it anymore. Now we want to deploy a new VM, so we have to clone this file again, file 1. So since the data hasn't changed in file 1, we can link it exactly to the same reference dnode. And all we have to do is just update the clone list of this dnode. And we are set. There is no problems at all here. So another thing which can happen is that we have modified our template virtual disk. So we need to basically now clone a disk which was a file which was already modified from the original. So this is basically where we have nested clones coming in. So in this demonstration, again, in the beginning, all the files point to the same data. Now, file 2, we modified some of the data of file 2, so now it points towards different data. So if you want to clone file 2, we need to create a new reference node, which is going to point to this new data. This reference node is going to have a ref node attribute, which is going to point towards the original reference node. And then the new file 3, and file 2 just cloned are going to point to this new reference node. And then we have to update all the clone lists and attributes to reflect it. So there is basically some problems with this approach. So the main problem is now if you want to traverse blocks in order without going twice over the same blocks, it becomes a little bit problematic. Especially with the ZFS send receive. ZFS send receive, when it's being implemented, it loses all information about block pointers and about TXGs. So our version of our dnode is out of the equation at this point. So there is one solution to go around this, is whenever we do ZFS send, we need to do multiple passes. So the first thing that we do is that we send our regular files, regular dnodes, and then we send our ref nodes, as shown here. And on the second pass, we're going to send basically clones of those reference nodes. So this way we do not need to send data twice, because we only send the private data of those new clones, and we reconstruct basically all the references from there. So the other solution to this problem is to have a slightly different approach for file cloning, which is called implicit references. So which is going to be included in this second part of the presentation. So implicit references basically here we're doing a contrast with direct references. Direct references, when we have new data here shown as B, it points directly to the shared data. With implicit references, we create a new special embedded pointer. So this embedded pointer, it doesn't point to any actual blocks on disk. It just says that the data is found somewhere, and there is some data, it's not just a whole. So whenever we basically stumble upon this kind of embedded block pointer, we have to go and look for the data in the list of ref nodes that we have for this clone. So here we're going to show an example read operation. So when we have a read operation, let's say we want to read data block 2 of our clone, and we start going from the top, And now we encounter this special call, and after we encounter it, we need to go look for data block 2 in our reference node. So we basically send the command to our reference node, it traverses the reference node, and then returns block 2 of our reference node. And that's the data that we're looking for. Whenever we overwrite data, we basically need to just make sure that we update which pointers are special calls. So there is a little bit more into it. We need to do a bunch of reads. It might affect performance, but this is basically, we don't really have time to discuss it in more details. So where the real problem comes is whenever we have nested clones. So if you have nested clones in one of your read, then we need to basically, if we don't find the data, we need to traverse every ref node one by one, going deeper and deeper. So let's say again we want to read the data block 1 of our clone. So we start traversing, we find the special call, then we go to the next ref node, we start traversing, we find a call, and we go to the third node. So basically if you have a 10-level nested clones, we now have to traverse 10 different ref nodes, which is sort of problematic. Fortunately, there is also a solution for that. So instead of basically just saying that the data is found somewhere, we actually say which ref node the data is found in. So right now, again, we're using the same block. We start from the top of the clone, we start traversing, we see that there is a special call, and here in our web block pointer, we can actually store which D node the data is available in. And it's available in the very first ref node, so we jump directly to it, and we return the data. For a case where we have several levels of nesting, this can be a very big performance advantage. So now, here's the analysis. Sorry, how much? Okay. So now for the analysis, we're going to compare the two methods, direct references and implicit references. So the advantage of direct references is that access time of blocks is basically the same as regular files. The disadvantage is that the ZFS receive becomes non-trivial and potentially slower. For the implicit references, accessing clones is potentially slower for each nesting level, and we have a higher arc footprint. Because right now, if basically we have to basically traverse not only the clones but also the reference nodes, and some blocks, some metadata blocks, reference nodes might not be actually referenced in any of our real clones anymore. So we have a higher arc footprint. Integration with other CSS features, I'm going to go quickly around it because basically there is not too much to say about it, except we need to create a couple of new data structures. For instance, for the zero, we need to make a new record type. For snapshots, logic shouldn't be too much protected. And for scrubbing and receive, it's easy to do with implicit references. It's a little bit more tricky with direct references. And finally, the ZFS feature flags, we want to make sure that clone is something which is downgradable. So if you delete all the clones in the file system, we're able to have this feature flag downgraded from active to inactive. Yes?
With the snapshots, is this issue with special pairs storage is that how you see as well?
Yes, basically the special pair mostly means that we have to, whenever we destroy, let's say, all the clones of the reference node, we must also destroy the reference node, must also free all the blocks of the reference node. So just make sure that we take care of all of that at the same time. Maybe there is extra problems. It shouldn't be an issue with that. Yeah, there shouldn't be basically an issue with that. So there is space models, so I totally took the research in that. The quick answer is that there is no easy solutions. It depends on what kind of approach we want to have. If you want to treat those new clones as copies, or if you want to treat those clones as references. So I'm going to basically skip over this slide because, to be honest, I don't really know what's the actual solution. Maybe it's something which is more of a discussion than whatever I would present. So I'm going to keep this for later. Okay, so for administrators, it would be very nice to be able to have some information about the reference nodes which are being created. So, for instance, let's say I make my VMs from some template. Let's say I lost my template, but I already have many clones which So basically, the way I see we can do this is if we create a new zap object in the root directory of the dataset, and we store the links to all the ref nodes which are present in this dataset, we could, by doing some hacks in the ZPL layer, we could make, basically show this this add zap object and show this as a little like small set of folders in the file. So basically what that means is that we create a special folder inside of the root dataset which is visible to the file system. And inside this folder we create one folder for each reference node. And inside this folder we have one file called content, so basically which is the original content of the clone, and the clones, which is a file which contains the relative paths to all the clones of this reference.
This is like your
.zfs for
like the .zfs snapshots, snapshots.
right, yeah.
You did a .zfs reference.
Yeah, exactly. It would be something like that. Yeah. So integration with operating system, this is just like how I imagine it should be integrated. So this goes for the very top user level. In FS, you have to implement the Pascal clone API, then make a libc clone function. You need a new system call, you could call it clone, or if you want to keep consistent with Linux, you could call reflink because they already have something similar for this. Then we need to change, add a new operation with the OP layer. And finally, we go to the Znode layer where we create, where we do all the basic, all the hardness. So there is some other thoughts which we're going to skip. There's basically some potential features we want to add to it. And finally, we have some comparing some other clone alternatives. So there is the duplication here is just sort of to show that it's basically solving some of the problems, but it's not a viable option for implementing the API set because it's not instant. On the other hand, linked dataset clones, this is something which could be potentially viable. So basically what happens is that whenever we clone a file, what we can do is we can, on the back end, we can create a new dataset which is going to contain this file only, so we make a dataset. And then we make a clone of this dataset. So we now have two versions of this file. And we create some links to those two different files in our original dataset. It's a little bit more complicated, but it might be worth exploring as an alternative because it might require less changes in the code. So that's about it. That's the Q&A. Yes. Sorry. It's only for the ZPL, yeah.
Why is that?
Why it's only more? Well, basically for the ZWall, we could implement for the ZWall if we really need to, but it's per file. So
Yeah, one thing I see is when we come here, it's kind of a lot of detailed options that you know, but you do kind of layer issue here, because there's really get the system happening. A lot of boarding
that's right. Like whenever we have to be a block, so this would require a little. Right, so that would require some additional changes. Yes.
We want to test what we would actually do in my optional that's actually called clone, not reference, despite it being called reference in the user activities. And when you actually just need ILC underscore clone, it's not very well documented. But I can point you to where that's
Yeah, sure. So anything else? Yes?
Currently, when you file on the snapshot, back into a whatever mode, copy back to the file system, you double the data. Be a method that you bring that swing to fast file copy, not double your data, something just big file on the snapshot.
Yes, well, what we're saying right now is basically similar to a file clone, but not file clone, sorry, dataset clone. So this would be essentially the way to do it right now. But our goal is to implement the AI API, which works only per file in one dataset. If we want to create several thousands of clones, we don't want to create a thousand of different data sets.
Right.
Yeah.
It could be used, a similar mechanism could be used to like copy files and snapshots. That's basically
What I'm looking at is.
You're talking about diluting, right, essentially, where you take a thing, like, there's
Well, I mean, even restore would be indicated from a snapshot. I want to copy, you know.
Oh, I see. So you want to
So
talk
you
about
make it-
like when you reference, like the instant reference,
Yeah.
rather than just having the object number, you can have the snapshot and the end object.
Right, yeah, we could have this as well if you would want to. I don't know like what the implications of it might be a little bit hard to implement, but it supports the show. Yes?
Another place this might be really useful for VMware is what they call subline snapshots, where instead of snapshotting an entire data set or one, you just snapshot the part of it that you want to copy. Block could use that as well as file, like VMware iSCSI or Fiber Channel.
Yes, yeah, of course.